Hey guys, welcome to the class today. So we're going to deal with chapter 15, sequential trade. So this is in Masculine, so you can also check there. The Masculine chapter is a bit bigger, so we're not gonna cover all topics there, so just this part, okay? Mainly, so as I mentioned last class, I'm gonna repeat some of the definitions. So in particular, sequential trade means that we're gonna start thinking about the states of the world. And then we're gonna have a consumer. I consumers is kind of a general equilibrium setup. Pure exchange, however, J firms and S states of the world. So states of the world, as I mentioned in the previous class, they can be thought as, for instance, being rainy or shiny, but in particular, they can cover anything. You know, for instance, tomorrow the new variant of COVID is Omicron, right? So that's already in the state S. So state S can be super comprehensive. Can also be very simple, like rainy and sunny. In particular, there is no restriction apart from all these sets being finite. The finiteness assumption is important. When you break it, a lot of the results we have here, they do not hold exactly, and then you have to do modifications. So a lot of macro is dealing with the infinite cases. So if you see this in macro, essentially, you will be seeing some infinite version of this. So there is some overlap here. It's fine, right? So, you know, sometimes some topics are so important that we have to cover them from different angles. So yeah, sequential trade and the arrow degree equilibrium are things that you also see in macro and sequential trade as well. Now, so here, the states of the world are unknown to the decision maker or consumer. However, they have beliefs over states. These beliefs are captured by pi, I sub s, and then the index I is for consumer and the index S is for state of the world. And then these beliefs happen to be subjective. So in this particular case, so there is no unique belief about the true state of the world. So this is a bit different from the expected utility chapter. Remember there that we were dealing with objective probabilities, right? So you were choosing over lotteries, and then each lottery was known essentially, they were common to everyone, and everyone knew the probability. Here instead, probabilities are indexed by I, which means that each individual has a subjective belief. So these lotteries are subjective, right? So in other words, these things are ambiguous states of the world. You don't know whether they will happen or not, and then you have a belief about their happening. For instance, with the Omicron variant, do we know whether or not we're going to be locked down in January? We don't know, right? So state of the world is lockdown, state of the world 2 is not lockdown. You have beliefs over that. My assessment right now is 50-50, right? Irina's assessment may be different, right? And then essentially that probability you assign over these two states is the pi, okay? Now, for every physical commodity, L from 1 to capital L, remember here we have physical commodities that are, you know, things such as an umbrella, a sun hat, and then you have states of the world, like sunny and rainy. And then here, however, we choose not over physical goods, but rather over arrow of the various securities or state contingent commodities. State contingent commodities are just a contract, a promise that you will be delivered a quantity of good L if a state of the world S happens. So I was telling you, for instance, this object here, the object of choice in this chapter, is essentially a contract that, for instance, will tell you, imagine an example with two states of the world, sunny and rainy, and sun hat and umbrella. This is a repetition of the previous class. I wasn't recording this, so this will be for your records. So essentially, you can have this X vector, and then the first entry will be 1, 1, which means getting an umbrella when it is raining, right? Entry, so vector 1, 2, essentially will tell you the quantity of sun hats that you get when it's raining. Sorry, it will be 2, 1. 2 is the physical good, so sun hat. The second subscript is the state of the world, rainy. So this will be the number of sun hats you get when it's raining. And then you will have again umbrellas when it's sunny, and then sun hats when it's sunny. And then for instance, these will have numbers there. So for instance, I can promise you one particular promise or contract or state contingent security commodity that will tell you 1, 0, 1, 0, 1, 0. So you get a sun hat when it's sunny and an umbrella when it's rainy, and you get nothing when the state is different from the object, right? And then you can create all kind of complicated contracts here. So the object here, as you can see, belongs to R L times S. So in practice, right, so we're dealing with this as a vector, but you could also rearrange this as a matrix, right? Because, for instance, you can think of being the columns being states and then the rows being physical goods. So you can easily rearrange this into a matrix. So these objects are very high dimensional, but right now we're vectorizing, right? So they become a very long vector. So yet again, I'm reiterating this because it's super important. Instead of choosing here over physical goods, as in chapter 3 in our study of consumer choice, here we choose over state contingent commodities. So state contingent commodities are these contracts or promises of goods that will be delivered to you when the state of the world is realized. So the trade that we're gonna study here is ex ante trade. So here you're just gonna trade on contracts, right? And then, you know, essentially all the consumption, all the general equilibrium is done ex ante. And then the state of the world is realized. So this will happen in day 0, time 0. And then in time 1, the state of the world will be realized and all payments will be made. So tomorrow, for instance, if it is in fact sunny, you will get a sun hat if you bought the state contingent commodity that deliver one sun hat when it is sunny. Okay, so essentially this will be about ex ante trade. Okay, now the state contingent, there will be also state contingent endowments for consumers. So essentially, because all of this trade is ex ante, there is also a physical description of what you will get an endowment, you know, ex ante. So this is not a real physical endowment, but rather a legal contract that will ensure that when you reach, you know, time 1, you will receive this physical quantity of the good. So as opposed to the X, omegas are not tradable, right? So these omegas are whatever you are given. So this is kind of a paper saying, you know, tomorrow Martin will receive a house, right? This is an inheritance kind of paper, right? So it's just a promise that, you know, a certain date you will receive something, but it's not still the house, right? The omega here are not physical goods, are still contracts, you know, promising, delivering goods, but they are not tradable. So these are things that you have as a property, but you don't trade them, okay? So they only belong to you, like an inheritance, right? So this declares that Martin will receive it, but nobody else, right? Once he receives the house, he can do whatever he wants with that, right? But before that, you know, this is just endowment. I'm describing, okay? Now, so preferences. So state contingent commodities, they have the issue that they are not physical goods, right? So they, on top, have this additional complexity that they have, they are described with respect to states of the world. Now, states of the world may not happen, and trade is ex ante. So you need to take into account the uncertainty, right? So we're gonna, this is an assumption. We're gonna choose to model this situation using expected utility model. This is not a pure expected utility model, it's subjective expected utility model, right? Now, of course, we don't want to be writing again and again subjective expected utility model, right? So we just say expected utility from now on. But notice that as opposed, you know, in stark opposition to what we did previously, right? Here, we don't have objective lotteries. We have instead subjective states of the world, right? And then we're really trading instead of lotteries, we're trading instead state contingent commodities, right? So it's, you know, it looks the same, but it is not, okay? So now using the subjective expected utility form, we declare that a full contract X is weakly preferred to X prime for some individual I, right? Whenever the expected utility, when I'm doing the weighted average, right, of these utilities that can depend on the state. So notice that at this level of generality, I'm allowing the U to depend on S. Yet another difference with the version of expected utility we studied. So in the version of the expected utility we studied previously, we didn't allow in most of the chapter the U to depend on the state of the world, right? We make it basically state independent, okay? Here instead, we can have different utilities per state of the world. So you can have different moods when it's sunny and when it's rainy, okay? Whatever, right? So you have the expected utility weighted by the probabilities of each state. And then when this expected utility is greater than or equal to the expected utility with respect to X prime contract, you declare the first one better than the other. Any questions right now? So this all is very straightforward. Now let's do technological possibilities. So technological possibilities are super easy mathematically, are hard to understand a little bit conceptually. So here you have, again, a production set that now is describing what the firm will do when it's sunny and when it is raining. So this production set here is also, a description of what the firm will do contingent of the states, right? For instance, this can mean that, for instance, if you have really good weather, you will have a high yield for strawberries, right? And this will exactly tell you that if it is really rainy, you will get lots of strawberries, right? And it's really sunny and dry, you won't get any, right? So whatever. So this Y describes essentially what the firm can produce, right? In each state, okay? And now you have a production plan, which is also state contingent production plan. That means that for every state of the world, it tells you what a firm will do. So again, for firms, this is essentially, they are fully rational, fully smart. So firms will be able to tell you what they will do contingent on every state of the world. So they are super planners. They know exactly what they will do tomorrow, right? And with respect to each state of the world. So this is a plan essentially. So the firms have plans and they fully commit to these plans and they implement them. So there is no uncertainty about whether or not firms will be able to produce these things in each state of the world. Do you understand? Okay. Okay. Now, what is an allocation? This is a monster, guys. So you have X star and Y star, which is of the size of the product of the XI production consumption spaces times the production sets. So this is a huge vector of size L times S parentheses I plus J. Okay, so this thing is huge, right? It's a super array with lots of entries. So this thing, is essentially a monster, right? So if you have, for instance, two goods, two states of the world, there you have four, right? So imagine you have two consumers and one firm, right? So then you have 12. So just with that simple textbook example, you have a commodity of size 12, right? So it can get super big, super easy, right? So usually the way we implement this in core exams is by assuming there is one physical good, right? And then essentially you will have two states of the world. So hence you will have the usual Edgeworth box, right? So you will have two states of the world times two consumers and zero firms, or the free disposal technology, which you don't count. And essentially you have then a 2 by 2, which is a simple Edgeworth box, okay? So remember that's a source of confusion I have noticed. So when people are given arrow-degree problems in the core exam, and they usually, in order to draw an Edgeworth box, usually you have to simplify because of the dimension. So then people fix the physical goods to one physical good. So in reality, there is only one physical good, but they add two states of the world. So they say good state, bad state, right? Or rainy or sunny. So usually, and then of course, the size of the state contingent commodity will be size 2, right? For each consumer. But it's because it has two states. And in fact, you're trading only one good, okay? This good usually is money, okay? Any questions there? Yeah, so this is just a warning so you don't get confused, right? So here you always have to make the separation between physical goods and states of the world, right? That's the only thing. And typically, when you do Edgeworth boxes that require low dimensions so you're able to draw with, then typically you assume that that you have just one physical good, such as money, and then of course the size of the vector is driven by the states. Okay. Now we're gonna define. By the way, so. And then we have a system of prices. Prices are as well a huge vector that is common for every physical good and every state. So in arrow-degree, because this is ex-ante trade, you have to have prices for every good, physical good, and every state of the world. So you have a price of the umbrella when it is rainy and a price of the umbrella when it is sunny, okay? And all these prices are ex-ante prices, right? So these are prices that you will trade, you will do the trading of the contingent commodities, the state contingent commodities, you will do it according to these state contingent prices, okay? And then you have this arrow-degree equilibrium whenever you have three conditions. First, every firm profit maximizes. Here, profit maximization is more interesting because this is profit maximization across all states. So this big product here is a product of the state contingent price times the state contingent production plan, right? So this is profit maximization across the states of the world, okay? It's ex ante profit maximization, okay? So remember this, right? Now, two, for every consumer, XI is maximal for the preferences, expected utility, given the budget set. The budget set essentially is endogenous, and then it receives prices times endowments. This is ex ante wealth because it's the multiplication of state contingent prices times state contingent wealth, omega. So this is ex ante wealth, right? And then you have the ex ante profits with the theta ij, okay? So all of this is done ex ante. Now, finally, you have market clearing. All the state contingent commodities have to be equal to all the state contingent production plans plus state contingent omegas, okay? Now, so this is arrow of the real equilibrium. Now, what is new? So it looks essentially like the previous equilibriums, right? What is the new thing? That now we have expected utility and now we have a state contingent trade, and this is all ex ante trade, okay? Now, time one, so after the trade is done, if the economy is in arrow of the real equilibrium, when uncertainty is realized, there is no incentive to trade further. So essentially, this follows from the first welfare theorem because the allocations are efficient, so they are Pareto optimal. So there is no incentive for anyone to trade because nobody can unilaterally, right, deviate from this. Essentially, they cannot have an allocation that is at the same time feasible and that is preferred for at least one person strictly, and for the rest the same. Okay. So in other words, just due to the first welfare theorem that is in full force here, you get that at time one, when uncertainty is realized, you get that there is no incentive to trade further. So that's really cool, right? Essentially, we're doing ex ante trade, right? Before uncertainty is realized, before tomorrow arrives, time one. And you don't know whether it's rainy or shiny. Irina has a different belief than me. I have a different belief. Martin has a different belief. All of us come together and we trade using these arrow diverse securities. And then, you know, magically, when actually tomorrow comes and then the rain or the sun comes out, right? We are happy with what we did, right? So that is really cool. So this is essentially a market that creates full insurance, okay? This is a keyword, full insurance, right? Essentially, this is a marvel, truly. So if we in fact had these state contingent commodities, then we can insure ourselves, you know, with respect to any contingency, right? So essentially, you know, in this magical economy, we come together and we're able to trade umbrellas and sun hats, such that tomorrow, irrespective of what happens, you're gonna be fully insured, right? Do you understand? Okay. Any questions here? Now, so all of this is too magical to be true, right? What are the issues here? So there is an assumption that we're making, and then macro people call it a name, that is called a complete markets assumption, okay? So we're assuming that essentially we can write state contingent commodities for every physical good in the world, okay? So now let's talk a little bit about real life, which is a bit weird for a theory class, right? But let's do it. So essentially, imagine, for instance, that you have, you're trying to buy insurance. Can you buy insurance for, you know, for renters insurance? In Canada, yes, you know. In Ecuador, for instance, I don't think we have them, right? If you are looking, for instance, for insurance for health, yes, you can buy them. Can you buy, for instance, insurance for your pet? Now you can in some countries, in others you cannot. But essentially, there are things you cannot insure against, right? For instance, you may have a really, you know, a really great video game that you don't want to lose, right? And it's a classical cartridge-based, you know, video game for Nintendo. You know, so you have a Mario, the original one. So and you really like it. You know, you don't want it to go, you know, to burn with a lightning strike or something. You want to insure it. Can you do it? Well, in some countries maybe, right? But in many countries, you cannot do it. So in general, it's very, in markets usually, it's very rare to have insurance for every single physical good, okay? So more developed economies, right? Essentially, eventually you get to create a state contingent commodities for all physical goods, right? Because the US is one such economy, so, so advanced in terms of financial development that you can write, financial instruments that are sort of the state contingent commodity, like for instance, futures, or derivatives, right? Where you can buy contracts specifying that you're going to get an amount of money, right? Which is a numeraire. In each stock of the world for any physical good or even event, right? Now, in other countries, especially very rural ones or rural areas, you cannot insure even your crops, right? So you want to harvest corn, you go and and plant a lot of corn seeds, and then essentially some countries you cannot buy insurance, you cannot sell the futures of corn, right? And then so complete markets are super hard to have in real life. So, and this is what's behind this, right? If you have complete markets, essentially you can trade a state contingent on everything and everyone will be happy, okay? Now, obviously, there is another big caveat here. So did you see that the dimension of these objects? So imagine a real economy, right? Even simplify that we have, 10 main goods, composite goods. So you have food, recreation, transport, gas and whatever. Now, with these 10 simple goods, how many states of the world there are right now? So, a lot of them, right? Now that the world is even more uncertain, right? So we have the variance, we have the economy, have politics, is Trump gonna win, a lot of states of the world, right? So what is the size of that vector, right? So imagine, even we simplify this to 10 possible scenarios. So it's 10 by 10, it's 100. So even then, 100 goods that you have to keep track is very hard. So what I mean by that is that this requires a lot of attention, right? Who among you is fully insured against all the states of the world right now? I don't think any of us, right? So you can buy, you can buy some stocks, you can buy some insurance here and there, but it's very hard to do. So in general, right, it requires lots of attention, lots of time, a lot of legal technology, right? Maybe at some time we can do it, but right now, this is more of a fiction, something that we would like to happen. So obviously this is nice, but it's very hard that it actually happens in real life. So the next thing we're gonna do is we're gonna see more realistic conditions under which we can achieve the essentially full insurance. And then we're gonna do it by sequential trade, okay? So here, what we did is called arrow of the real equilibrium. Now we're gonna move to a new thing called Radner's equilibrium. And essentially the setup is slightly different. And it has the main thing that you have now, complete markets. You just have one commodity that you're gonna trade. So you can insure with respect to one commodity. So consider a case where there are not S markets, but only one good that can be traded at time zero. So ex ante, you can trade on one good. So for instance, pick one numeric good. So right now we're gonna trade using, cocoa beans, right? So cocoa beans is gonna be our numeraire, and we're gonna trade on that. Now consumers make prediction about the spot prices. So spot prices are gonna be state contingent prices for future events, rainy or shiny, at time one. And then the consumer can only trade on the physical good, cocoa beans in time zero. Then the consumer trades the only state contingent commodity at prices Q. Q is the price of the cocoa beans. And then essentially this price will change across the states of the world. So cocoa beans will have price 1 if tomorrow is sunny. And if tomorrow is rainy, it will have price 2. Okay. So Q is a state contingent price. Yeah.
One question. So we are reducing the number of physical commodities to one, but we are
no, you still have L commodities, but you can only trade ex ante on one commodity alone. So there are still L commodities. So all of them are the same as before, but you choose one that everyone agrees you can trade ex ante. Okay.
Okay, but we are making the problem intertemporal.
Yeah. So now it happens in 2 periods instead of just in time zero. So now you're going to maximize. So this guy, consumer, and with utility UI, again, expected utility V1, is going to maximize the consumption across the states of the all commodities. So you can see here X1 to XL, right? And now this consumer is going to do it essentially maximizing also with respect to the Z commodity. Z commodity is going to be the only commodity you can trade ex ante, and this is going to be such that if I multiply the quantity of Z that I have per state of the world times the spot prices QS and sum it up across S, it has to be less than or equal to 0. So this means essentially that you are transferring amounts of this physical commodity multiplied by a price, spot price, across the states of the world, right? So essentially, the only role that this set commodity has is that you have the constraint that you cannot go short, right? So essentially, if you say you gamble that tomorrow is going to be rainy, right? Then essentially this has to balance out such that whatever quantity you have when it's sunny, right, multiplied by the price, have to add up to 0. Now, the budget here is a spot budget. So this is the price with respect to price S multiplied by the quantity of S has to be less than or equal to the price of the state S multiplied by the omega S plus P1S, which is the price in time 1 of the cocoa beans multiplied by the quantity of ZS of the cocoa beans I have in that state of the world. And essentially, this is the endogenous budget. And now what you have here is that you want to maximize, essentially, this is a plan for all the states of the world. So in that sense, it's sequential. So this looks eerily similar to something you have seen in macro. So have you seen the consumption in time? So if you relabel the state by time, right? Essentially, you have a very similar program, right? So you are maximizing in that case, for instance, discounted utility, right? Subject to very similar budgets, right? So you have the flow constraint. That will be restriction number 2. So if you replace S by time, this looks very similar to the flow constraint in macro, right? And then this is kind of a balance constraint where essentially you have that this only good that you're trading has to add up to 0 when multiplied by the spot prices. Now, so let me say what is a Radner's equilibrium. A Radner equilibrium is a collection formed by a price vector. This is the price of the cocoa beans for a state contingent commodity, the first good at time 0, and then the spot price vector. So the spot price vector is just a prediction of the consumers for every state of the world and every consumer I. Consumption plans are, again, the physical good you're trading ex ante and whatever you intend to consume in tomorrow or given the state at time 1. And this constitutes a Radner's equilibrium if every consumer solves the problem we just stated above. So they are utility maximizers in this dynamic sense in one or state contingent sense. And then you have a market clearing condition such that the sum of all the holdings you have of the only physical good you're allowed to trade, so the ZSI, so the cocoa beans, is less than or equal than 0. And then that the total amount of physical physical consumptions, right, for every state of the world of the physical good XSI is less than or equal than the total amounts of such good in terms of endowment. Okay. And then also we have to make 2 normalizations. The first thing is that the prices of the good one, the cocoa beans in the time 1, have to be equal to 1, and the price of the cocoa beans in the first state of the world is equal to 1. Okay. These are normalization. This means that they don't matter because of homogeneity of degree 0, but these are a way for us to prove without ambiguity. So we're going to maintain these assumptions from now on. Okay. That is just a normalization. Because of homogeneity of degree 0, they don't matter. Okay. So now, here is the punchline of the chapter. This is a very short chapter. The punchline is the following. You can have essentially the same outcome as with the error of the Ryu general equilibrium with ex-ante trade, and you can achieve the same with the Radner's equilibrium. So what is good here is that you don't need, these full complete markets as long as you can have a state of the world that can be traded across all states. Okay. This is still a lot. I'm going to discuss this later. So we're still asking a lot economy, because you have basically to be able to buy insurance for cocoa beans, right? For all the states of the world. And that's very hard to achieve in real life, right? Because you have to consider all possible states. Now, without further ado, let's continue. So if the allocation X star of this size, L times S times I, and the contingent commodity price vector P of size L times S constitute an arrow degree equilibrium, then there are prices Q of size S for contingent first good commodity, so this is for cocoa beans, and consumption plans for this commodity Z, such that X star, Z star, Q, and P constitute a Radner's equilibrium. So essentially what this is saying is that if you have an Arrow's degree equilibrium, you can create out of that a Radner's, okay? So that's less impressive because we know Arrow degree is already huge, right? So it has markets for every state and for every physical commodity. So the fact that it can produce a Radner's is not that impressive. The impressive thing is the following. Conversely, if the consumption plans X star and Z star and the prices Q and P constitute a Radner's equilibrium, then there are multipliers mu1 dot mu s, one per state of the world, and such that they are positive, such that the allocation X star and the contingent commodities price vector mu1 times P1 dot mu s times PS. So this is a scale up new price vector, constitute a narrow debris equilibrium. So essentially, these multipliers are interpreted as the value at time 0 of $1 at time 1. So this is changing essentially, the value ex post to the value ex ante. But other than that, this thing is telling me something super important and impressive. This is telling me that you can implement all the goodness of the arrow debris equilibrium with this much simplified version of the Radner's. Essentially, if you allow to trade in one physical good, but across all possible states, remember this is the key assumption now, you can still achieve the Pareto optimality of the Arrow's degree. So essentially, you can get exactly the same as Arrow's degree. Okay. So any questions about the content of the theorem and a proposition? Then we go to the proof. But essentially, are you getting why this is important? Essentially, with Arrow's degree, we assume complete markets in a very strong way. So we assume that you can essentially buy state contingent commodities for all physical goods and for all states. So that can be a lot, right? So you cannot insure, all possible physical goods. So now we're making a less stringent assumption that you can now just insure with respect to one physical good, but still with respect to all possible states of the world, okay? All contingencies, okay? Now, this is still a lot, but it's less than Arrow's degree. So Radner's requires much less than Arrow's degree. However, we have shown that we're going to show, but we have at least make the proposition that when you have a Radner's allocation, then essentially you can reconstitute or recreate an Arrow's degree with the goodness that comes from it. So essentially, nobody wants to trade anymore. You are Pareto optimal allocation, you're great, right? So I'm going to focus the proof on part 2, right? Let's do everything, right? So 1 means that if you are Arrow's degree, you are Radner. So if we have an Arrow's degree equilibrium, we have to build what? So remember that Arrow's degree is a pair of X and a price. So you have X and P, and you need to build Z and Q. What is Z and Q? Q is the ex ante price of the physical commodity we're trading, so the cocoa beans price, Q, size S. And what is the Z? Is the state contingent, claims to cocoa beans. Okay. Now, so what we want to do is we want to show that we can build out of the Arrow degree these 2 additional objects. So we're gonna do that. Now, first of all, we can let the QS of P equal to P1S for every S. Now, with this, we claim that for all individuals, the budget set for the arrow degree problem is essentially this excess, such that the multiplication of PS times the parentheses of xi, the physical good, minus the omega, the endowment, state contingent endowment, is less than equal than 0. This, in fact, is identical to the Ratner's budget constraint, because you can see here that we can build this set Si by the following operation: 1 divided by the P1S multiplied by the price of S multiplied by XSI minus omega Si. With this construction, you can essentially see that when I plug in, and with this equality, right, that QS is equal to P1S, you can plug it in here, and you will check essentially this is reproducing this budget. Now, to see this, suppose that Xi belongs to the arrow degree budget. Now, for every S, we denote the set as I mentioned. Then we have that QS multiplied by ZS is equal to PS multiplied by the multiplication of the commodities minus endowment, which is the budget. And then it has to be that PS multiplied by XSI minus omega Si is equal to P1 ZSI, more or less. So we know that this also belongs to the Ratner's. The reverse is also true if we have something that is in the Ratner's budget constraint. That is, for some set, we have that the summation of the nominal value of the claims to the cocoa beans is less than or equal than 0, and that the state contingent budget holds for all states. Summing up over S, we reproduce essentially the arrow's degree. Okay. So once we have established that the following sets are equivalent, so the budget in the arrow degree is equal to the budget in the Ratner's, then with the arrow degree, we essentially set a new equilibrium, a Ratner's one, by fixing Q equal to P11 dot 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 P1S. So this is the price of the physical good one, cocoa beans, from state 1 to S, according to the arrow degree. And then the spot price is P1 dot 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 PS, and the contingent state price set 1 to dot 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 set S, defined by the following product, as I mentioned before. And essentially with this, I have built the Z and the Q. Now, note that the contingent market is clear, since for every state of the world, if I take the summation over these state contingent commodities, I can just take out the price that does not depend on the individual, and then this will mean that I have here this market clearing condition for the arrow degree. Now, so this is a very simple proof that shows that arrow degree can induce a Ratner's. Now, for the other side, the converse, now we have to create these multipliers that, remember, the role was to bring the ex post value of physical goods to the ex ante values. Okay, so we're going to choose mu such that they help the following equation to hold. So mu S is equal to QS divided by P1S. In other words, I take the Q price of the physical cocoa beans of state S, and then I divide it by the price of the physical good cocoa beans in state S according to the prediction exposed time 1. And when I divide that, essentially this is translating future prices, right, into time 0. Okay, so time 1 prices into time 0. So this is the mu by definition. Now, remember that the only thing we have to do for creating our arrow degree is showing that I can build an X star and a price that is the contingent price, such that they satisfy the 3 conditions above. We can write essentially the Ratner's budget set for every consumer I as all the commodities in space L times S, such that for all set cocoa beans, the nominal value of the cocoa beans is less than or equal to 0 for across the states, and the budget constraint now multiplied by mu S PS parentheses XS minus omega S is less than or equal to QS set S, and then essentially we can write this as the arrow degree budget by adding up across the states. Hence, the consumption plan XI is also preference maximizing in the budget set of the arrow degree. Since this is true for all consumers, we conclude that the price vector with the multipliers clears, and then essentially you have a arrow degree equilibrium. So none of these proofs is super hard. there's a conceptual point here being made. A conceptual point is that you don't need to create a state contingent commodities for every physical good, okay? You just need one good as long as you can insure against every possible contingency. Now, so you will say, okay, this is great. So then, you know, as long as we have one good that you can insure against all possible states of the world, we're fine. But the real reason, you know, that people have to still study these kind of markets is that, you know, there is a violation of this when you cannot insure against all possible states of the world. And then you have to study something called incomplete markets. So incomplete markets are essentially a description where you can insure against, for instance, rainy and sunny, but you have a third state that says, you know, floodings coming from, you know, atmospheric rivers, and that is not covered, you know, within the possible insurance that you can buy. So there are some states of the world against which, you know, a lot of insurance do not work. So there are catastrophic events, right? Or they are unspecified events that your insurance will not cover you, right? So essentially, this is breaking this assumption. So what I'm telling you is that the assumption that you can insure even in one good with respect to all possible states of the world, you know, is a big assumption. It's a strong assumption. Now, if you happen to have at least one good that you can insure against all possible states of the world, then you're fine, you know, as long as you're rational and as long as you're fully attentive. But essentially, you're fine. Okay. So
I have a question.
Yeah.
I'm a little lost, but I'm wondering, for Arrow-Debreu equilibrium, whatever price you have there, is that price actually a composition of all the possible Radnor prices over all the possible states kind of locked into one Arrow-Debreu price? And is that roughly why the Arrow-Debreu equilibrium and the Radnor's equilibrium are equivalent? Or maybe it has nothing to do with that and I need to take another look.
Yeah, so, you know, exactly the relation between the prices in the Radnors and in the Arrow-Debreu are given by this proposition. So you can see precisely that for the first one, if you have an Arrow-Debreu, the price in the Arrow-Debreu constitutes the same price, spot price prediction in the Radnors. So here, essentially, you have consumers that have perfect foresight, right? So these guys are able to essentially be able to predict, you know, the same prices as they happen in trade ex ante in the Arrow-Debreu. So the magic of the Radnor is essentially that you use the set commodity, the first commodity, cocoa beans, to be able to transfer resources, right, across the states of the world, right? So essentially, by moving those resources, you are changing the budget in a way that essentially will reproduce all aspects of the Arrow-Debreu. So you get essentially the same predictions. The spot prices predictions correspond to the Arrow-Debreu actual prices exactly. Okay, so that's why this is very important. Now you can see the math here. You can go to the notes and check it. You can also read Mascolelli if you want to. But essentially, you know, what we're showing is that the way we write the Radnors, even if it's happening in time, is essentially an exact equivalent description of the Arrow-Debreu budget, right? So it turns out that mathematically, the two sets, the budget in the Arrow-Debreu and the budget in the Radnors, are one and the same, right? So they are just written differently, and of course they have different interpretations, but mathematically they correspond to the same set, okay? That's the main reason. Now, when you have a Radnors and then you want to move to an Arrow-Debreu, then you have to make a slight change to prices, because remember, these prices are predictions, right? So now in the Radnors. So now you need to bring them to ex ante values by means of this multiplier mu1 to mu_s. Okay? So these multipliers, essentially, as we define them in the part 2 of the proof, they are the exchange rate between prices time 1, right, and prices at time 0, right? So this is essentially the only difference between the two. Okay? So spot prices are future prices, right, predictions. And then essentially, you know, Radnors are predictions. Arrow-Debreu are actual prices. They happen in a static setup, and they are exchanged, you know, typical Edgeworth box-like prices. They don't have anything special, okay? Radnors are predictions. However, you know, magically in this world, you know, it happens that the spot predictions are one and the same to the ones that you have actually next ante trade. Modulo, the exchange rate, right? Mu. Okay. And that's essentially the relation between the two. Okay. Any other question?
Good.
Okay. So what I wanted to tell you guys is, yeah, go ahead.
Optimization problems are not the same either.
No.
So we have to do we have to do a mapping of each of them or not?
So this is notation from Mascolet, right? Which is a lot, notation. But remember that the utilities are assumed to be the same. This capital U is describing the expected utility, right? So in order to make the notation even clearer, right? So we don't have any ambiguity when you study this. So essentially here, we have this UI of xi, which is essentially, equal to the expected utility, right? So when we go to the Ratners, right, we write with this capital U, which is a notation by Mascolet of expected utility. And then essentially, this is maximizing the same expected utility, right? And then the only thing that is described in a different way is the budgets, right? So the budgets are in principle different. The proof that we made shows that both budgets are one not the same, up to scaling, right? With this muse, okay? So the only thing we had to prove was that the budget was the same because the optimization, the objective value, is already the same, okay? Now, one important thing. So here there is some confusion sometimes when you overlap this knowledge with the one you given in macro. So in macro you study the same kind of sequential equilibrium, but when you don't have states, rather you have time. Or sometimes even in the black belt version of macro you study with time and states. So a composition of them. Now that can turn this a little bit different, but the principle is the same. So the only thing it will change is that here, in the expected utility, you will possibly have also a discount factor, right? But essentially, this works under the assumption that both in the Ratners and in the Arrow-Debreu, the objective is the same. So the utility is the same, okay? As long as you're maximizing the same preference, right? Since we have shown that the Arrow-Debreu budget is the same as the Arrow-Debreu, as the Ratner's budget, then, with the assumption that the objective is the same in both cases, then you have always the same outcome, right? So essentially the underlying assumption here is you have the same preferences in both worlds, okay? That's the only thing. So the intuition, again, is not that hard. So these cocoa beans, the only good you're allowed to insure against, essentially allows you to transfer resources from one state to the other, right? And this is essentially mathematically what allows me to convert the Ratner's sequential budget into the Arrow-Debreu comprehensive budget, right? Because of this adding up of the QS times ZS across all the states, this is essentially the transfer of resources across all the states of the world. So, and this will allow me to essentially put together and cram it into the Arrow-Debreu budget, which is essentially just the summation of the states. So you can see here, right, essentially, that this apparently innocent product in the Arrow-Debreu is in fact a summation of all the state budgets, right? Because here you have in a very long vector, block vector, you have prices of each state of the world multiplied by a commodity of a state S, plus, and then added up over the states of the world. So a different notation here will essentially mean this is a summation, right, of a state budgets added up over states. Do you understand? So the only thing that is hard about this chapter, which is the short one, is that the notation sometimes is too compact. So this is hiding essentially the fact that this is a summation over state-dependent budgets, right? So this inner product between prices and X's, remember that prices are state contingent and X's are state contingent, right? So the inner product is essentially can be alternatively written as the summation over states of P sub S times X sub S. Do you understand? So this inner product is essentially an adding up over budgets. And what essentially allows me to have the same outcome, essentially the same set in the Radners, is this condition, right? That I can move resources around using Z, and then this set will enter in the budget, moving essentially the income in arbitrary ways. So you can move through the Z resources from rainy to sunny in arbitrary ways, okay? That's essentially what allows you to do all the magic here, okay? So that's it. That's the chapter, and maybe now I'm gonna take any questions, and then essentially we're done. So I'm gonna have the recording 10 more minutes, and then I'm gonna stop. Okay. Let me know if you have any questions. Okay, guys. So I'm gonna stop recording now.